All right, so let's get started. Good morning. Welcome to the last class. We've all made it. So, all right, any questions before we start? What we're going to do today is just continue on our review, sort of use the gradients quizzes as a way to see what problems that we are not very sure with. I do want to bring up our topics slide here. Yeah, we're going this way, right? And then we'll do that. And other announcements. I have not yet posted the gradients aggregate scores. I'll do that today, and then you can sort of check those. All right. Okay, so let's get started. Right. Last time we were talking about logistic regression, and I said, there are a couple of questions that you need to be aware of, like what is the difference between discriminative and generative classification, and then what is the difference between logistic and linear regression, right? Because both have the name regression in it, but both do very different things. Okay, so I'll move to kernel methods unless there are any questions about logistic regression. Yes. Yeah. Oh, okay. Now, of course, yeah. So the question is, let me just pull that up. How do you do the training for logistic regression for multi-class case, right? That's the question. Yeah, I don't think I went through it, even though it was like a problem in like an extra credit thing for programming assignment 3. Yeah, I mean, that won't be covered in for the exam, sure. But if you do want to know how to do that, the idea is fairly simple. So this is what the multi-class logistic regression looks like, right? So for every weight vector, so you have, let's say you have k classes, so you'll have k weight vectors, right? And each weight vector, when it is combined with your input data in this way, so there is no sigmoid in multi-class logistic regression. This is just an expression which is exp of this over the whole thing, and this you can verify easily that this will always be between 0 and 1, right? So you can think of this as a probability of the data point x to be in class J, right? And now how do you train it? The training is fairly similar. So the loss function, right, that's the main thing that you need to know. The loss function is still kind of the same, except that there are not two classes now, right? So you have k classes, right, which means that you will have k values for y. So think of the same 0 to 1 of k encoding that you did for neural networks. So you will have k values for y, and then you'll multiply that with log of theta j. So yj log of theta j. So what will happen is that your only one of those yj's will be 1, because that's the class, and then you just multiply with that. So that will become your loss function. So you can sort of do the derivation. I think in the assignment, I'm trying to see, assignment 3, the extra credit, right? Yeah. So here is the loss function for that. If you have k classes, actually this is right, it's the loss function, negative log likelihood. So you can use that, but for the exam, don't worry about it. Any other questions about logistic regression? Okay, so let's quickly jump to kernel methods. So kernel methods are very interesting, right? Yes. Right. So yeah, so if you remember, we had a small discussion, and this is more of a philosophical discussion on difference between generative and discriminative classifiers, right? So the idea behind generative classifiers is, so both are trying to predict the same thing, right? Both are trying to say what is y given x, right? So the form is this, or the type of functionality you need from either of them is the same. You need to find out what is y given x, or they are probabilistic. You need to find what is the probability distribution for y given x, right? So either y could be binary, in which you want to find what is probability of y to be 1 or 2 given x, or y could be continuous. Now there are two ways to solve this. One is using this sort of Bayes rule, right, in which you say that py given x is px given y times py px, right? So the idea here is that you first find what this is. So this is probability of x, your input, given your class, right? So this is what we call the generative distribution. So using this, you can actually generate new inputs, right? So to get the final probability, which is py given x, you apply Bayes rule. So you first compute this, then you multiply it with the prior of y times sort of the marginalized value of this pxy. I mean, this is just a normalization thing, right? So this is one way, and this is what we do in naive Bayes or QDA or LDA, where we explicitly compute this. But if you look at linear regression or logistic regression, right, we never compute this px given y. We have a direct formula for what is py given x. So let's think of logistic regression. In logistic regression, what we do is so in logistic regression, we say that py given x is sigmoid of w transpose x. Right, so we are directly computing py given x, or py equal to 1 given x, right? Whereas in naive Bayes or QDA, we say that py given x is px given y times py divided by just a summation over all possible values of y, or integral if this is continuous, right? So here is the difference. Here we are explicitly computing this, here we are not. So that is the difference. And the reason they are different in terms of, like, okay, so people have asked the question, which one is better? Is discriminative better than generative? And it has been studied in statistical learning theory that the VC dimension of this model, a discriminative classifier, is always less than the VC dimension of this. Now, if you remember our discussion on VC dimension kind of ties with the generalizability, right? So if you keep the VC dimension of your model small, your model is expected to do better in a sort of a testing scenario, whereas this one might not do as well. So that is a difference. So that's why typically discriminative models are preferred. But now somebody would say, why use generative models at all, right? The benefit of these models is that because you have this distribution, they are easy to understand, they're easy to interpret, right? So you can understand, okay, this is what the distribution for x is for this class, distribution for this class, so you can do more with this. But if you just need to do this part, only this, then going this extra step is an overkill. You're doing more to do the same thing, right? And remember, I gave you an example about learning languages or distinguishing between sounds, right? So that's the discussion. All right, so that let's bring it up. This one? Oh, what is it? Okay, so Occam's razor is a concept which basically says that if you have two models, right, and both are giving same performance on your training data, but one is more complex than other, then always go for the simpler model. So it sort of follows a general philosophy of keep it simple, right? So, and we have seen that over and over again, right, with the regularization, trying to reduce the magnitude of weights. So what statistical learning theory says is that if your VC dimension is small, right, that also means that you're kind of applying the Occam's razor. You're going towards simpler solutions. And that is why discriminative classifiers or logistic regression is preferred, because it's kind of following the principle of Occam's razor, keeping it simple. Any other questions? All right, so let's move to the next topic, which is kernel methods. And in kernel methods, the main thing you need to understand is that why do we do kernel methods, right? Or why are kernel methods used, right? And we have seen that the main there are two advantages. One is that it lets us map data into a nonlinear space and lets us use linear models in nonlinear scenarios. So, for example, if you think about regression, if I do kernel methods, if I use kernel regression, then instead of learning a straight line, I could learn curves, which is good. The other advantage of kernel methods is that because it works with these kernel matrices, right? So we never work with the data itself. We always work with a kernel matrix, which is in principle obtained by applying a kernel function. That's why it's called a kernel method, because there's a core function there on every pair of data, which means that the data need not be d-dimensional vector data, right? It could be any other data, as long as you have some way of computing the similarity or the distance, right? So that is why we use kernel function. So that is one thing. The other thing you need to understand is that what is kernel trick? So I mentioned this kernel trick in the context of several algorithms like linear regression and support vector machines, right? So the kernel trick essentially says is that you can do the whole learning and inference and everything. You can use a classifier or a regression model without really explicitly applying the kernel function, which means that you can do everything just using the K matrix. So that is the principal idea, right? So that's the kernel trick. And then we also talked about different kernel functions, so you can look at the slides for those, right? And what are the properties that you need to know. There was one particular kernel function that we used a lot, which is radial basis function, or the Gaussian kernel, which essentially says exp minus difference in the L2 norm divided by some 2 or something, right? Or the gamma, right? And you have done a lot of experiments in your programming assignment 3 with support vector machines where you use the RBF kernel, right? So one thing you need to remember, I've been talking about that what RBF kernel essentially does is it maps data into an infinite space and then does a linear model there and then brings it back. But because of the kernel trick, we never explicitly take it up and bring it back. We are just working with your K matrix. So you need to also understand it in the context of support vector machines, right? So if you remember, the support vector machines by themselves are pretty easy, right? It's just W transpose X plus B. If it is greater than 0, you call it positive class, less than 0, negative class. But because of the way we solve it, right, because we are trying to maximize the margin, right, that's one difference. And the second thing is that when we were trying to solve that optimization problem, instead of solving it as a core constrained problem, right, we converted it into a dual form, right? Remember, we introduced these Lagrangian multipliers and then converted it into a dual form. Why did we do that? The reason we did that was that after we did that, we could apply the kernel trick. So that is one important thing that you need to sort of really understand. And I'm trying to remember where it was. Right. So I mean, this is a very interesting discussion. Not just for the exam, right? Aha, here it is, right? So the reason SVMs, we can apply the kernel trick to support vector machines is because of this formulation. If we had the original formulation, which was this, right, where we did minimize this term subject to these constraints, we could solve it, right, just in this form, because it's just a constraint optimization problem. But by changing it into a dual problem like this, what we see is that every x now occurs as an inner product with another x, which means that we can replace this with a kernel function. And same thing, I think I showed you that after you compute your W, right, the W, now when you want to get the prediction, you will do W transpose X star, which means you'll do Xn transpose X star. So you can apply the kernel trick there as well. So the thing to remember is that not every machine learning algorithm is amenable to kernel tricks. Like, you cannot apply the kernel trick to every machine learning algorithm. What you need to show is that in that machine learning algorithm, whenever you have X, it occurs as an inner product with another X. Only then you can apply the kernel trick. So SVMs, you could do that. I think I showed it for linear regression as well. Any questions about kernel methods in general? We have a couple of questions in gradients, but they are sort of fairly easy to understand, right? So I give you a kernel function, right? And then I say just apply it to get the new data and then use that. So, okay, you can open that homework. Right. Right. So these kind of problems, the only thing you need to understand is, okay, I have to apply this kernel function to every pair of data objects. Okay. So let's go back to the topics. So kernel function is okay. Maximum margin classification, I think you have done a lot of problems on that. So the idea is that, so this is support vector machines, right? So the idea is that you have some data and you're trying to draw a line, and you're trying to draw a line that not only separates your data well, but also maximizes the margin, right? So you need to understand what is the notion of a margin, right? And what is the equation of a line, and then how do you compute the value of the margin, right? So the way to draw the margin, and I think there's one problem that I really like in this quiz that all of you have looked at, where you is forced to draw the margin, right? So the idea is that if I give you some data, let's say these are my positive points and these are my negative points. So if I give you equation of a line, you can draw that, right? Draw the line. Now, how do you find what is the margin, right? So the margin will move your line in either direction, right, parallel to this. And wherever you point, so let's say it's a negative point. So this would be left side margin, right? And then the right side margin or the other side margin would be exactly symmetric to this. So you don't have to move this line all the way to the positive point, it will be here. So if I give you equation of a line and the data, then I am basically fixing the margin as well, right? You can't change the line anymore. But let's say I give you just the slope of the line, right? Then you can adjust the margin a little, because slope just determines the slope of this line, right? Where it is with respect to the origin is determined by B, right? So if I just give you the slope of the line and say, draw the line that will give you the maximum margin, then what you need to do is you say, hey, let me try this. Let's say this was your negative, positive point. I give you the slope of a line. So the line could be this, anything. So what you do is you say, okay, let me draw one line that touches the first positive point, right? You can't go below this because then you would be making a mistake. Here I'm assuming this is a linearly separable case. So this could be one margin, you say, right? So then what you can do is you can say, what will be the opposite margin? Because once you know this, then you can figure out what the opposite. And at the right decision boundary, right? And then you can measure your. And then you say, okay, instead of this, what if I had started with this as my left margin and then went ahead? So whichever gives you a higher margin will be your desired boundary, right? So that is the idea. So do practice that problem again. That gives you a good sense, okay? So another thing that you want to remember is that this is just a side hint that, when you have to specify equation of any line, you can do that using two unknowns, and B, slope and intercept. But whenever we talk about equation of a line in the sense of a support vector machine, we always say it is W transpose X plus B equal to 0. Where, okay, let's do this. X2 equal to MX1B, right? So let's say this is X2. This is a vector, so we write it like this: W1 X1 plus W2 X2 plus B equal to 0, which means it has 3 and B, right? So and that basically means that this equation is over specified in the sense that you multiply this with any constant. I can multiply 4, and it will be the same line, right? And that is why there's a little bit of confusion. But the thing that you need to remember is that the equation of this line should always be written as W transpose X plus B equal to 0. Equation of the positive margin should be written as, and negative margin should be written as long as you remember this, that should be fine, that you could work with that. Okay, so the kind of problems that you could expect here are, of course, drawing the line and finding the margin. That's one. Another is that where we ask you to compute the slack, right? I think you had a problem in gradients as well, where I say that the data is not linearly separable, right? But I give you the equation of the line, and I also give you the margins, right? Well, once I give you equation of the line, then you have the margin too. So if you ask you to compute the slack, so the thing you want to remember is that the slack is essentially only computed for the points that are on the wrong side of the margin. Okay, so going back to our right. So let's say this is our decision boundary. These are two things, and so there are some points that are on wrong side of the margin. So these 2 points are on the wrong side of their margin. These 2 points are on the wrong side of their margin. So you only compute the slack for those, right? And you don't even have to do any geometry here. So there's an exact equation for computing the slack, right? Which is slack is essentially 1 minus this quantity. That's the slack, right? And if the slack is negative, then you make it 0, because negative slack means that that point was on the correct side of the margin, so you ignore those. So you can easily compute the slack just by applying this formula. So this is the first, I haven't written it in that form, but slack is, for any data point, slack is just 1 minus y and W transpose xn plus b, right? And if slack is less than 0, then set it to 0. That's the formula, right? So in that problem, all you need to do is, for every data point, you just compute this, right? And now what will happen is that, let's say I give you a problem like this in the class, right? In the exam, let's say like this, and I say compute the slack. The first thing you should understand is that you don't really have to compute the slack for these values. It will be 0, right? So just compute it for these 4, and that's it. That will save you a lot of time, because these will always be less than 0. And how do you get that is fairly easy. So the formula that I gave you is essentially measuring the length of these lines, and that's, if you just look at it a little more carefully, you'll see why it is so. All right, any questions about this part? Okay, very good. So that kind of is what we want to look at maximum margin classification for. Another thing you want to remember is, what are support vectors, right? And why are they important, right? So support vectors are the points that are on the margin, if it's a linearly separable case, and they are the points that are on the margin and between the margin. So in this example, all these points, this 1, 2, 3, 4, 5, 6, 7, 8, are the support vectors. Why are they called support vectors? Because if you solve the optimization problem that we looked at earlier, the Lagrangian multipliers for only these points will be non-zero. Every other point, for all of these points, the Lagrangian multiplier that you will learn by solving the the optimization problem, by solving this problem, right? All the alpha n's will be 0 if the point is not on the margin. And the reason they are useful is because then you only need those to compute your W, because alpha n will be 0 for others. So you only need to store those alpha n's, and you only need to store, that's it. Those are the things you need to store, right? Any questions about that? Okay. And that actually is a good one of the very interesting properties of support vector machines is that they give you such a compact model, right? Because you won't expect all the points to lie on the margin. Only a few will lie on the margin or between the margin, and that will be enough for you to get predictions. Okay, so that was this Slack we talked about. Role of scenes, SVM learning. I think this is, you're fairly comfortable with this from the programming assignment. This kind of controls the bias variance, right? How complicated your surface is versus how much training error you're ready to accept. Of course, we talked about the kernel trick and support vectors. Okay, any questions before I jump to the next topic? Cool. All right. Okay, then we jumped into this whole business of unsupervised learning, or as I like to call it, latent variable modeling, right? And we looked at a bunch of different ways to understand data, because now we have no labels, so we cannot learn any regression model or a classification model, right? All we have is a bunch of data, and we need to just make sense out of it, right? So one problem that has been posed in that context is what we call clustering, where I give you data, and I want you to give me some partitioning of this data such that things in one partition are similar to each other, or more similar to each other than with other points in other partitions, right? So we looked at one algorithm which is easy to understand, k-means clustering, and we have looked at some problems about that. So the only thing you need to understand in k-means clustering is that there are two steps. You start with your initial centroids, you assign points to the closest centroids, recompute your centroids, and keep doing that. So I don't think that, I mean, look at all the problems and gradients about that, but you know, I don't see it has a big problem, right? Unless there are questions. Okay. Okay. One thing that we also looked at was spectral clustering, and here I've introduced it here. I mean, I should have talked about spectral clustering with k-means clustering, because there are two ways of doing clustering, but because spectral clustering needed us to understand sort of the spectral properties of a matrix, so I waited until we did the other topics. But the problem is still the same. I give you data, you have to partition it, but in spectral clustering, what we do is we sort of construct this graph, right? So look at the notes that I have, but the general recipe is fairly easy. So you have data, you compute the pairwise distance of similarity, and then you find the k closest neighbors for every point, and use that to construct a graph, right? Once you have the graph, after that what you do is same even if you just started with a graph. Right? So you have the graph, which means that you have the adjacency matrix, so you can compute the Laplacian of that matrix. So look up what are the properties of the Laplacian of a graph, right? Of a adjacency matrix of a graph. Things like what is the first eigenvalue, what is the smallest eigenvalue, and so on. And then what we do is we look at the smallest eigenvalues, not the largest. The smallest eigenvalues, look at the eigenvectors corresponding to those, and they will tell us what are the clusters in this graph, or what are the components in the graph, right? So that is general idea. So go through sort of the algorithm that I have in the notes, and that should make it easy to understand. Questions about, yeah? The other way. So you take the adjacency matrix, you construct a diagonal matrix, do the degree in the diagonals, right? The row sum. You do d minus w, d minus w. So that's the Laplacian. So there's nothing like really fancy about it, but the point is that if you do the spectral analysis of that, the eigenvalue decomposition of that, it tells you where are the components and so on. So that's why it's so important. Okay, all right. Then came the really interesting topic of EM and mixture models, right? So this is one thing that you might want to look up a little more, and do try the example that I have in gradient, and also look at the workbook that I have, and we have the code for that too, right? So the general idea behind latent variable models is of course clear, right? You have some hidden variable z, and you assume that x that you observe is coming out of z, and this is all probabilistic. It's a nice Bayesian structure. So what you say is that hidden variable z is a random variable, which means that we have some probability distribution for that, and then the observed variable x is also a random variable whose parameters of that model, that distribution, are a function of z, right? So that is the general idea. So they are all connected. But the interesting problem is that if I knew z, or if I knew all the parameters of my model, I could get x. But I want to go the other way around. I have x, and I want to estimate the parameters of my distribution. And we also saw how this could be used for clustering, right? Because if you treat z as a categorical variable which can take values between 1 and k, and if you infer this z, right, then essentially what you're getting is that for every x, you're getting a value, a number between 1 and k, which is what we need in clustering as well, right? So it is interesting. Now, the interesting part is how do you do the parameter estimation, right? And that, I think, is a very interesting and very important part in machine learning, right? How do you do parameter estimation in the presence of hidden variables, right? And one thing that we saw was that it's not like it's magic, right? You can write out the expression for the log likelihood of the data, which looks like this, right? So in principle, I could solve for theta by maximizing this, because it's a mathematical expression which I could maximize. But there are some issues with this, right? One issue is that you have a summation inside a log, which always freaks mathematicians out, because you can't put the log inside, and if you want to do the derivatives of this expression, it becomes a mess. That's one issue, but that's not the main issue. The main issue is that, if you remember, I had a notebook where I showed that if you look at this, this function, so this is a function of some parameters, right? So if you plot this function, you will see that it has multiple modes, and that's where it becomes a little tricky to optimize on, because if you do gradient descent, it would get stuck in one of those local optimas. So that's the issue, and because of that, there is another approach, which is EM, and that's the sort of the whole thing. So expectation maximization, right? So to get a sense of what it is. So there are two ways to understand EM. One is you can just figure out, okay, what are the steps to do EM for Gaussian mixture models, which is easy, and that's probably what you need to know for the exam and to solve those gradients problems as well, which is that you have an E step, but you also want to understand sort of the general philosophy, right? So the idea is that I have some hidden variables z, I don't know what they are, right? And they are connected to x. So what I do is I first assume some initial estimates for my parameters, right? Theta. Then using those initial estimates, I find what is the log likelihood of my data, right? Now I cannot directly compute the log likelihood of my data, because the log likelihood of the data contains x and z. I know what x is, but I don't know what z is, right? So instead of doing that, what I can do is I can compute the expectation of my log likelihood, because I don't know what z is, but I know what the probability distribution for z is given my initial estimates, right? So I compute the expectation in each step, and then I maximize that to get new parameter estimates. So that's the M step. So EM, we keep doing that until we converge, right? What happens for Gaussian mixture model, and that's the one that you need to be more sort of familiar with for the exam, is that because everything is so nice, right? You have it takes k values, and then everything is Gaussian. So what happens is that the E step becomes nothing but computing these responsibilities, RIKs. So for every data point I, and for every mixture component k, you just need to compute RIK, right? So you need to understand how to compute that, and it's not that hard, right? So you know what pi k is. Pi k is the probability of the kth component. That we already assume that we know, and then this is just the PDF of a Gaussian, right? So one thing you want to remember is the PDF of a Gaussian always. There's a PDF of a Gaussian, so you can compute all of these values. So that's the E step, and in M step, what you do is you use these RIKs to re-estimate all of your things in theta. So theta has all the pi k's, mu k's, and sigma k's. You can do that again, and then you keep doing that. So in the gradients problem, of course, I don't want you to keep doing this over and over and over again, but maybe I could ask you to do it for one step, one EM step, right? So you need to know how this works. Any questions about this? Okay, very cool. And of course, there's some discussion I had about the relationship between k-means and EM, and it's kind of easy to see, right? Both have this iterative step. First step, you assign points. Second step, you re-estimate your parameters. So k-means also does kind of the same thing. All right. So that was that. Then the next topic we had was factor analysis, which was sort of a generalization of mixture models. In mixture models, we assume that our Z can take 1 out of k values. So essentially what you're saying is that your data is coming from 1 out of k components. But in factor analysis, what we say is that Z could also be a vector of infinite possible values, right? I mean, a vector of L elements, and each element could take infinite values. So of course, now it is no longer a mixture model. So you can't use it for mixture modeling, but what we can use it is for getting these hidden factors in the data. And we have look at one of the examples that I showed in class about the cars example. So the idea is that you have some high dimensional data in D dimensions, but you assume that it is actually represented using only L factors. So what we essentially are assuming is that in truth, the data was generated, there are only L factors that sort of describe the data. But what you observe are some combinations of these L factors, some different types of combinations. So that's actually a general assumption behind factor analysis or dimensionality reduction or latent variable modeling itself, right? So the idea is that the generative process looks like this. You have some L factors, Z1, Z2, ZL, and this is what describes a data object, right? This is the true data that exists in this L dimensional space. But what you observe are some linear combinations of these. So you'll have some X1, X2, XD observed, where X1 is some linear combination of this, W1, Z1 plus W2, Z2 plus, and we don't know what these are. And same way X2 is this, right? So what we need to do is, given observed data, so this is one data point, so this is vector X. Given lots of these data points, we need to infer what these weights are, right? And then we need to infer what these are, because that way, that's what dimensionality reduction is. But in factor analysis, we are more interested with these weights, because these weights tell us how is each observed feature related to these true values, because with that we can make some semantic assessments about those factors. We can say, if you remember the example I gave, right? So I had this data about cars, and each car was represented using 12 features. But what we saw was that there are 3 hidden factors that describe cars. So there is, like mileage and cost and engine, right? And then all of these observed features were some linear combinations of these. So that helps us understand the data a little more. Okay, and then what we did was we also looked at one special form of factor analysis, and what we showed was that if you put some constraints on the parameters of the factor analysis, then you get PCA, probabilistic principal component analysis, and then we jumped into principal component analysis, right? And that is another thing that you need to understand. So what is PCA? PCA is a way of reducing the dimensionality of the data, right? So you have data in D dimensions, but we want data in L dimensions. So what PCA does is it gives you that reduction and also gives you some guarantees. It says that if you do PCA, then and you look at the variance of each reduced dimension, the variance will be maximal if you do PCA. If you do something else, of a similar form, like similar linear combination, you would not get that much variance. So that's the classical PCA theorem, right? So the idea is that if I give you some data, right, and if I give you some principal components, then the thing that you would because of the classical PCA theorem is that if I embed my data on this principal component, then the variance that I get is the most. And you know how to compute variance, I'm assuming. But the variance that you get by embedding data on the first principal component will be the largest. You cannot come up with any other linear combination to get the embedding in one dimension, which will give you larger larger variance than what the first principal component will give you. So that is one thing you want to remember about principal component analysis. And the second is how you do it, right? So the idea is that you have some data, you center it, right? You subtract the column means, and then you compute the covariance matrix, you do the eigenvalue decomposition, and then you take the principal components for the highest eigenvalues, or the eigenvectors corresponding to the highest eigenvalues, and those are what we call principal components, right? Of course, in the exam, I will never give you, I'll never ask you to compute eigenvalue decomposition. I also don't know how to do it beyond a 2x2 matrix. So we will not ask you that. What you need to understand is which eigenvalues to use or which eigenvectors to use, right? So that is sort of the thing that you need to remember. Any questions? Okay. Then we also look at singular value decomposition, SVD, which is nothing but a way to reduce the rank of a given matrix, right? So that's more of a mathematical operation. But the reason we were looking at it here was that SVD also lets us sort of represent data in a different way, and it helps us in image compression. We saw that. Then we also saw how we can use it for as a recommender system. So if I have data about people buying stuff, how do I and I want to recommend more things to buy, we can do that using SVD. And that's, in fact, some of the earlier recommender systems used SVD like that, right? Another reason that we looked at SVD was because you can use SVD to do PCA. So some equivalence that you need to be aware of. So if you look at the slides, it'll be clear. So the idea is that if I had a matrix X and I did the PCA thing, right? I computed the covariance matrix and then I looked at the eigenvalues of that covariance matrix. Those will be same as if you did the SVD of X. There is no covariance matrix in SVD, right? You did the SVD of X and you looked at the first left singular vector, right? So there is equivalence there. So you can use SVD for PCA. Spectral clustering is here again. But yeah, so spectral clustering I told you earlier, right? The main thing you want to remember is that the notion of that Laplacian matrix and how looking at the smallest eigenvalues can give you information about the components. Any questions? Yes, go ahead. LDA and QDA. Yeah, that is not covered in the midterm, right? You could. I mean, of course, I will not ask you to do MLE on data, right? That's too much. But what we could ask you is for a simple, I mean, so let's say I give you two. Try to remember, yeah. So let's say I give you two class conditional densities, and I want you to tell me, given a new data point, which class does it belong to? So that's QDA, right? Or LDA, right? So yeah, that could come. Yeah. But that's simply applying that Bayes rule formula that I showed earlier. Py given x is px given y times py. And in the class, one thing you want to remember is that even though some of the problems might seem like they have too much of computation, but try to figure out how can you avoid computations, right? So maybe you do not want to compute the denominator in many cases because you need to compare, right? Sometimes it might be easier to compute the log and then add it up rather than multiplying things. Sometimes you can ignore a lot of data points because you know they are not going to figure it. So those are the things, if you know those, you can do the exam much faster. There will be 30 problems in 3 hours, right? So 6 minutes per problem. So some of the problems, if you know those tricks, you can do them much faster. But if you go brute force, compute everything for every point, then you might need more time. The simple answer to your question was yes. Any other questions about the exam or life in general? And of course, the TAs are right now grading programming assignment 3, and they should be done next week. Early, I don't know, have they posted it? I don't know if they've checked. That's probably not, but I'll try to ask them to do it by Sunday evening. So if you have questions about that, you can talk to the TAs. And of course, the exam will be on Wednesday, and then we should be able to grade it and post the grades by Thursday or Friday. And I'll be around, so if you have questions about that, you can come back. What else? And then I'll send you the instructions for the exam. They're same as the midterm. Exam is here. You will get a seat number and the version number, so you bring your picture ID and everything. So I'll send you that information. But other than that, yeah, I mean, I don't have any office hours on Monday, but if you want, you can post anything on Piazza. We'll try to respond as much as we can. Yeah, so that's probably the end. I just want to end with just thanking the TAs. So if you get a chance to meet your TAs, please thank them as well, because they've been doing a fabulous job. It's a very large class with 280 students. We have 4 TAs, but I think they've been trying to, they have done a tremendous job in sort of managing everything, grading and so on. So that's certainly something that please, thank them when you see them. Otherwise, yeah, it's been fun teaching this course. So thank you very much for all your questions and your participation. I always enjoy teaching this class, this course, and I particularly enjoyed teaching this particular class as well. So if you are a senior, congratulations, and I'll hopefully see you at the commencement. And if you're not graduating, then I'll see you next semester.